so this is the first video in a series I'm doing about modular forms. Now, before we jump into the thick of it, there's a couple things I want to go over. First off is prerequisites. Absolutely essential for this course. You will need some experience with complex analysis, so understanding the basics of holomorphic and meromorphic complex functions and integration of complex functions. Absolutely essential for this course. You'll probably need some background in abstract algebra. I mean, at least vector spaces and inner products for sure. Also some experience with group theory is going to be important. Of course, as we get on in the series, other things will get introduced and you may realize, oh, this is a topic I have to go back and read up on. So the most essential thing to have to even just get started is complex analysis. Also, for the very beginning, perhaps not completely essential, but I would recommend some experience with geometry, both differential and algebraic geometry. Again, right now, not absolutely essential that you have those things to get going, but as we get deeper into this course, those are going to be pretty important aspects. Now, some of those things I will introduce and bring up in my other series, the geometry of SL2Z. I'm going to keep that going sort of separate to this, but really it's kind of two sides of the same coin. This series, for now, is going to talk more about modular forms themselves as functions and the vector spaces of modular forms. Whereas the geometry of SL2Z will maybe focus more on the geometry a bit. So we'll talk about things, maybe elliptic curves in more detail, Riemann surfaces, and ultimately modular curves. So of course these things dovetail and they are intertwined. Anyways, with all of that stuff out of the way, it's time to travel to the Platonic realm! So the first thing we need to do is review the definition of weakly modular functions. And in order to do that, I'll remind you about the definition of Mobius transformations. So given a matrix A, B, C, D, which we write as gamma for shorthand, which belongs to the group SL2C, that is the group of 2x2 complex valued matrices with determinant equal to 1, we define the action of the matrix gamma on a complex number to send it to AZ plus B over CZ plus D. Now, of course, this only makes sense if the denominator is non-zero. That is, if Z is not equal to negative D over C. Otherwise, if the denominator is 0, this expression won't be defined, but if we imagine taking the limit as the denominator tends towards 0, the expression should increase towards infinity, so we'll just define this to be infinity in this case. Now, of course, since we're tossing infinity into our set, so we're not just acting on the complex numbers, but we're now acting on the complex numbers union infinity, that means that we also need to describe the action of gamma on the point at infinity. So again, the first thing we do is we appeal to our sensibilities about limits. If we look at this expression AZ plus B over CZ plus D, if we imagine taking the limit as Z approaches infinity, this quantity should be A over C. So this will define it to be A over C, of course, if C is not equal to 0. And otherwise, if C were equal to 0 by a similar argument, it would make sense that this would give us a fixed point. So we would map back to infinity here. Okay, so that's the definition of a Mobius transformation. So now a weakly modular function, this is going to be a function which is defined on the upper half complex plane. So this is the set of all complex numbers whose imaginary part is strictly greater than 0. And it can take on any complex value. And we're going to ask this function be meromorphic. So that means it's holomorphic everywhere except for some collection of points which do not accumulate together. Furthermore, we're going to ask that it obey the condition where if we were to take f of gamma acting on Z, where gamma is the matrix ABCD, this becomes CZ plus D to the power of k multiplied by fz, And we want this condition to hold for all, not the entire SL2C, but just the group SL2Z, and of course everything in the upper half complex plane. Now this integer k, this is going to depend on the function f, and we call it the weight of f. So what I've defined here is really the weight k weakly modular functions. Now, for our purposes, at least for the forefront of this series, we will restrict only to integer values of k. And notice one thing right off the bat: if k is odd, then our transformation property tells us that f of gamma z, this is equal to cz plus d to the power of k multiplied by fz. But as one can check, given our definition from the above, a matrix and its negative have exactly the same action. So this is the same thing as negative gamma acting on z, which would end up, given our transformation law, which would be negative cz minus d to the power of k multiplied by fz. And then since k is odd, the negative sign comes out in front, and we're left with cz plus d to the power of k multiplied by fz. But now we have an expression and its negative being equal to each other. And the only possibility is, since these matrices are arbitrary, the only possibility is that the function itself has to be 0. So there's no interesting weakly modular functions of odd weight. Therefore, we'll primarily be sticking to weakly modular functions of even weight. Now, it turns out that this action, this SL2Z, this actually defines a group action on the vector space of functions on the complex upper half plane. So clearly this is a vector space over the complex numbers. If you add two functions on the upper half plane together, you still get a function on the upper half plane. And of course, we can take complex scalar multiples. So here, the action is going to be prescribed in the following way. Given some matrix of SL2Z, we define the weight k operator to be, so f, taking the weight k operator with the matrix gamma, this is going to be cz plus d to the negative k multiplied by f gamma z. So if we look at the transformation property that our weakly modular functions are supposed to satisfy, the weakly modular functions are precisely those which are invariant under this action. So we just get the exact same function back. So in order to verify this is a group action, we need to check that the identity matrix acts trivially and that the composition of the group action respects the group operation. So first off, the weight k operator of the identity matrix, well, c would be equal to 0 and d would be equal to 1. So the term out in front is just 1. And one can check, of course, that gamma would just send z to z, and so we find that, yes, in fact, the identity matrix acts trivially. In order to prove that the group action respects the group product, we're going to define what's called the factor of automorphy. So the factor of automorphy for a entry of SL2Z and a complex number z, this is simply going to be cz plus d. All right, and so now we're going to prove a composition law for the factor of automorphy. So if I have two matrices gamma and gamma prime, the factor of automorphy for z, well, this is the factor of automorphy writing out the entries of this matrix. We have a, b, c, d, multiplied by a prime, b prime, c prime, and d prime. And multiplying these out, given our definition of the factor of automorphy, I'm really only concerned with the bottom entries here. So I'm only going to write the bottom entries of this matrix. So a prime c plus c prime d, and then the second bottom entry is b prime c plus d prime. And I'll just put dots in the top entries. And of course, this is all for z. Well, in this case, if we expand out this factor of automorphy, then that means we have A prime plus C prime times D multiplied by Z plus B prime C plus D prime. Alternatively, suppose I were to look at, I were to take the product of factors of automorphy of gamma prime Z, and the factor of automorphy for gamma prime Z. So this becomes C multiplied by gamma prime Z. So expanding that out would be A prime Z plus B prime over C prime Z plus D prime plus D. So that is this factor of automorphy here. And that whole quantity is multiplied by the other factor of automorphy, which is C prime Z plus D prime. So if I were to multiply this expression into the brackets, what I'm left with is C A prime Z plus C B prime plus C prime D Z plus D prime. And now if one looks at the above expression that we obtained, we see we have all the exact same terms as this expression down here. Therefore, what we've shown is that the multiple of these two factors of automorphies down below is the factor of automorphy above. These are equal. And this thing is called a cocycle condition. The reason for this terminology is might be familiar if you've ever studied homology or cohomology. One talks about cycles and cocycles. And the reason why this is called a cocycle condition is because this way of the composition law factoring as this product, this sort of mimics the way that cocycles come up in different cohomology theories. But if you don't know anything about that, not to worry, that is not going to be essential information for us. Okay, so now that we've proved this condition on our cocycles, this will allow us to prove that this group action respects the group law. So if I were to take the weight K operator of the product of the matrices gamma and gamma prime of our function f, well, writing this out, this would be the factor of automorphy comes out in front with gamma prime, and Z, and this would go to the power of negative K. And of course we have inside we have both these matrices acting on Z. And now using our cocycle condition, we can break this expression open to the factor of automorphy of gamma on gamma prime Z to the negative K multiplied by the factor of automorphy of gamma prime Z to the negative K. Now I would like to pull the gamma out and express it as one of these weight something operators acting on F. And one thing I can do to keep things equal without having to introduce a different factor of automorphy is I can write this as the weight 0 operator, because the weight just controls the power of automorphy out in front, and if that was to the power of 0, it would just be multiplication by 1. So I can write this as the weight 0 operator of gamma acting on this function f, whose argument is gamma prime z. But now, if I reconsider this expression, what do I have out front here? Well, I have exactly the factor of automorphy of weight k for gamma and gamma prime, where gamma prime z is the argument. Here, gamma prime z is the argument, and here I have the matrix gamma as part of the operator. So I can rewrite this expression. I still have my factor of automorphy for gamma prime z out in front, but I can rewrite this expression as the weight k operator of gamma acting on gamma prime z. And then finally, looking at this expression again, I can, since I have gamma prime acting on z, and I have here my factor of automorphy of gamma prime and z out front here, this is really just the weight k operator of gamma prime acting on this. So I have the weight k operator of gamma acting on f, and the weight k operator of gamma prime acting on f, all for the argument z. And thus we've shown that the group action does respect composition of elements in the group. Okay, now since the group SL2Z is pretty important, we're going to have a shorthand for it. So we'll often write this as either gamma or gamma naught as a shorthand for SL2Z. And recall from my geometry of SL2Z series, this group is generated by the matrices S and T, where S is equal to 0, negative 1, 1, 0, and T is the matrix 1, 1, 0, 1. In particular, the way that these matrices act on elements under Mobius transformations is S sends Z to minus 1 over Z, and T sends Z to Z plus 1. And since these matrices generate all of SL2Z, in order to check that a function is a weakly modular function, one only needs to check the condition on the generators to ensure that this is the case. In particular, one need only check that f of minus 1 z is equal to z to the k multiplied by f of z, and that f of z plus 1 is equal to f of z. So this tells us, the second condition tells us that all our functions are periodic of period 1, at least in terms of the real numbers, and this will have consequences for us when in the next video when we talk about Fourier series and the importance of that to the general theory. So now to take the next step from weakly modular functions to modular functions, let's consider a map Q, which is going to go from the complex upper half plane to the punctured unit disk. So here, remember the open unit disk is simply the collection of all complex numbers such that the norm is strictly less than 1. And notation that I like to use, well, this is somewhat common. By writing a hat, one can oftentimes mean that you're adding in a point at infinity. I also like to use, conversely, a check to mean that I'm removing the origin or 0. So when I write d check, I mean all the complex numbers whose norm is strictly between 0 and 1. And this map is going to take the complex number z, and send it to e to the 2 pi I z. So to check that this is indeed a map to the punctured unit disk, observe that e to the 2 pi I z in complex norm, well, this is the complex norm of e 2 pi I multiplied by the real part of z plus the imaginary part of z multiplied by I. So factoring this out, we get that this is e to the 2 pi multiplied by I, so I'm multiplying everything into the parentheses here, multiplied by the real part of z. And since the norm is multiplicative, I can write this as the product of these two norms here. But recall that e to the I times any real number, that is a complex number of norm 1. So this quantity here is just 1, and the second term is e to the power of negative 2 pi imaginary part of z. And since we're assuming that z is in the complex upper half plane, that means the imaginary part of z is strictly greater than 0, and therefore this is e to a negative exponent, so it's strictly less than 1. And of course, e to any exponent is greater than 0, so we do see that in fact this complex number has norms strictly between 0 and 1. Not only is this map well defined, but it is also surjective. So if I were to consider some point w, which is in the punctured unit disk, and I take the complex logarithm of it, let's look at the imaginary part of the complex log. Oh, in particular, the complex log over 2 pi I. So of course, there's some arbitrariness here where this depends on choosing a particular branch for our logarithm. But of course, we can always do this to whatever specifications we need. And I'm going to multiply this expression by 1 by multiplying it by negative I over negative I. So this becomes the imaginary part of negative I. And now I'm going to expand out the complex logarithm So this becomes the real log of the norm of W plus I theta, where again theta depends on our particular branch cut for the logarithm, all over 2 pi. Now, multiplying negative I into the parentheses, we see that in the second term with the theta, the i's are going to cancel each other out, and we'll have something purely real. So that will be killed by taking the imaginary part. So what we're left with is, of course, this factor of 2 pi in the denominator. And then the only part that's imaginary is going to be this log of norm W, and of course the minus sign is coming along with it. So we have negative log norm W over 2 pi. But since W is in the punctured unit disk, its norm is strictly less than 1. And therefore, log is strictly negative for any such W. And so this entire expression is strictly positive. Therefore, the imaginary part of log W over 2 pi is strictly greater than 0. Thus, log W over 2 pi I belongs to the complex upper half plane, and we can see that our map Q, of course, we chose this as the inverse of W, so we can see that Q does in fact map this to W. Therefore, this map Q is surjective. Now, this map isn't injective. However, if one recalls from basic complex analysis that two quantities e to the 2 pi iz and e to the 2 pi iw, these two will only be equal if w and z differ by some integer. This is easy enough to check by, say, writing out the complex polar form in terms of sine and cosine. Therefore, we get a map q tilde, which takes, if we mod out integer translates of the complex upper half plane, this gives us a map to the punctured disk, which is a bijection. So we suppose then that we have some weakly modular function defined on the complex upper half plane. So in particular, this function is going to be meromorphic. Then we're going to define a function f tilde on the complex, the punctured complex open disk. But we need to remove a couple other points because since f may just be meromorphic, we want to remove the poles. So we're going to take out rather the images of the poles under our map Q. So this complex function will be given by, for some element d belonging to this punctured disk, we're going to define f tilde at w to just be f of log norm w over 2 pi I. Now, this does appear to introduce an ambiguity in terms of the branch cut. However, this is still well defined because our complex exponentials, the preimages are only the same if it differs by some integer translate. And recall that if our function f is meromorphic, it must satisfy the condition that f of z plus 1 is equal to f of z. So it doesn't discriminate between integer translates, and thus this is in fact well defined. So finally, I give you the definition of modular functions in general. We can drop the weakly. So what this is it is a weakly modular function f, such that the induced function f tilde is meromorphic on the entirety of D, not just D puncture. Now, part of the inspiration for why one may want to consider these modular functions does come from the geometry of SL2C series that I have. But first, let's just consider the punctured open disk. So if we had a function defined everywhere, or meromorphic everywhere, there may be some poles, but it's not defined. We don't know anything about what's going on at the origin. It's very tempting to just want to have this point to fill it in. But as in my geometry of SL2Z series, when we take the quotient of the complex upper half plane by the action of the Mobius transformations of SL2Z, we get this
fundamental domain where this bottom arch is the complex unit circle and the lines are positive, real part positive 1/2, real part negative 1/2. We realized that this space was not compact, and we wanted to take the compactification by adding some point at infinity. And if one considers our map Q going from the complex upper half plane down to our punctured disk, the points that are closer and closer to infinity along the strip correspond to points that are closer and closer to this origin. So since we want our space to have a point at infinity and we want our functions to also be defined everywhere, including this point at infinity, in terms of the punctured disk, that corresponds to having our functions be defined, or at worst having a pole at what would be the origin of the punctured disk, or the point at infinity for SL2Z acting on the upper half plane. And this is precisely why we want the induced function to be meromorphic on the entire open disk. So in particular, since it's meromorphic on the entire disk, this also means that we can't have poles of this function accumulating towards the origin. That means that we also can't have infinitely many poles as we go up in the region, the fundamental region for the action of SL2Z on H. In other words, if f is in fact a modular function, that means that there exists some bound, say m sub f, such that f has no poles in the region of complex numbers whose imaginary part is strictly greater than this bound. So all the poles will be contained within some compact subset of the fundamental domain. So that's going to do it for this video. Next time we're going to talk about Fourier series. In particular, since these modular functions are periodic, we're going to get Fourier expansions for these modular functions. And this will allow us to also define modular forms. So we'll finally get to that definition in the next video. And then in the one after that, we should be looking at some examples, explicit examples.